this video is on using scientific notation. It's lesson 37 in your book on pages 230 through 235. So why do we use scientific notation? Scientific notation is super handy when we're writing very large or very small numbers. For instance, if we're looking at weight of the Earth weighs this many kilograms. Now that is an enormous number, and having to keep track of all those zeros can get a little bit ridiculous. But if you put it in scientific notation, it's 5.98 times 10 to the 24th kilograms. Much easier to write. Or, how much does a hydrogen atom weigh in grams? One hydrogen atom weighs 1 AMU, and 1 AMU, or atomic mass unit, is 1.66 times 10 to the negative 24th grams. So if you're going to write that without scientific notation, here's the number we're looking at. All these zeros with a 166 at the end. Again, it's really hard to keep track of all those zeros. You're going to mess something up somewhere. Plus, 1.66 times 10 to the negative 24th is way easier to write. So what is scientific notation? Scientific notation is a number written as the product of two factors, and it's always written in the form a times 10 to the nth power. So a is some number that's greater than or equal to 1 and less than 10. So it's some number between 1 and 10. It can be 1, but it can't be 10. And n is an integer. Alright, so here's some examples. We're going to put these in our notebook. We want to write each of these numbers in scientific notation. So we need to write these numbers as a product of some number between 1 and 10 times 10 to a power. So here's how we do it. We decide where can we put a decimal point in this number that will give us a number between 1 and 10. Well, if I put it here, still bigger than 10, here, still bigger than 10, here, here, here. But if I put a decimal point right here, that gives me 1.234. That is between 1 and 10. So 1.234 is going to be my A. Now, I have to multiply that by 10 to a power to get it back to this 1,234,000. So the way that I figure out what power of 10 I'm using is to count how many units and in which direction I have to move this decimal point I inserted back to the original decimal point. So here's the one that I put in. Here's the original decimal point. I have to move this decimal point 1, 2, 3, 4, 5, 6 units to the right. Now, since it's to the right, it's positive, and the number of units I moved it was 6. So my power of 10 is positive 6. So it's 1.234 times 10 to the 6th power. Now in example number 2, this number is actually smaller than a number between 1 and 10. I need to find a point where I can put a decimal point that will make this number between 1 and 10. So if I move it right here, still smaller than 1. But if I move it right here, I have 3.06. That's my A. That's my number that's between 1 and 10, 3.06. Now to get it back to my original number, I'm going to have to multiply it by a power of 10. Now, here's my decimal point that I put in. Here's the original decimal point. To get it back to where it started, I have to move this decimal point 2 places, so 2 is going to be my power of 10, and since I moved it 2 to the left, my power of 10 is negative. So 0.0306 in scientific notation is 3.06 times 10 to the negative 2 power. Here's another example. In this case, we want to find the product and write the answer in scientific notation. Now, when I do this, notice that I have 5.82 times 10 to the third times 6.13 times 10 to the 11th. Now, this is all multiplication, So I can actually use the commutative property to help me solve this. So what I'm really doing here is 5.82 times 10 to the third times 6.13 times 10 to the 11th. Now, this is commutative because it's multiplication, so watch this. I can go 5.82 times 6.13 times 10 to the third times 10 to the 11th. Now, I'm going to need to multiply the 5.82 and the 6.13, but check out this on the right here. I have 10 to the third times 10 to the 11th. Now, those have the same base, and when I'm multiplying two numbers with the same base, I can add their exponents. So I know that the left part of my answer here is going to be times 10 to the 3 plus 11, or the 14th. Now I just have to figure out what 5.82 times 6.13 is. So when I multiply those, I get 35.676. Or 677 if I round it properly. So I have 35.677 times 10 to the 14th. Now, this is close to our answer. However, it's not actually our complete answer because it says write the answer in scientific notation. Now, this number right here that we're multiplying by 10 to a power needs to be between 1 and 10, but it's bigger than 10. So I need to find a place where I can put a decimal point that will make this number between 1 and 10. So I'm going to put that decimal point right there. So my new number is 3.5677. Now, in order to get this decimal point back to where I started, I have to move it to the right 1. Now, I already had a power of 14, but I moved to the right 1, which means I need to add 1 to my power of 10. So my answer in scientific notation is 3.5677 times 10 to the 14 plus 1 power, or the 15th power. So whenever something's already in scientific notation, and you need to move the decimal point to make a between 1 and 10, if you move the decimal point to the right to get it back to the original place, then you add that many. If you move it to the left to get it back to the original place, then you subtract that many. Here's another example that needs to be in your notebook. We want to find the quotient here and write the answer in scientific notation. Now, we do have 7.29 and 8.1, but look at this. We have 10 to the negative second divided by 10 to the negative sixth. Now, we have like bases, so we can actually subtract their exponent. So part of our answer is going to be 10 to the negative 2 minus negative 6 power. Like bases being divided, we can subtract their exponents. So negative 2 minus negative 6 is the same as plus 6. So we have 10 to the 4th as part of our answer. Now we'll simply divide 7.29 by 8.1. And that gets us 0.9. Now, this looks like it's in scientific notation. However, A here is not, because it's not between 1 and 10. So in order to get this to be something between 1 and 10, I actually have to put my decimal point after the 9. So I have 9 times 10 to a power. Now, my power before was 4. In order to get this decimal point that I put in back to its original place, I have to move it to the left 1 unit. So I'm going to subtract 1 from the power I had before. That means my answer in scientific notation is 9 times 10 to the 4 minus 1, or the 3rd power. Now we're going to compare these two expressions. Before we can compare them, we need to simplify them. So I'm going to simplify the first one, simplify the second one, and then use one of these symbols to compare them. Now, just like before, I need to divide 4.56 by 3. That gives me 1.52, and then I know I'm going to have a times 10 in scientific notation. Now I'm dividing 10 to the 9th divided by 10 to the 5th. I can subtract my exponents. 9 minus 5 is 4. So I have 1.52 times 10 to the 4th. On this side, I want to divide 5.2 by 1.3. That gives me 4. I'm going to be multiplying by a power of 10, and since I'm dividing these powers of 10, I subtract their exponents. 8 minus 5 is 3. So I have 4 times 10 to the 3rd. Now I need to compare these. In order to get these back into their original form, I need to use these powers of 10. Now, a positive power of 10 tells me that I need to move this decimal point to the right that many places. So 1.52 times 10 to the 4th, if I move to the right 4 places, 1, 2, 3, 4, actually gives me 15200, or 15,200. 4 times 10 to the 3rd, positive 3, tells me I need to move my decimal point right here 3 places, 1, 2, 3, and that gives me 4,000. Now, which one is bigger? Obviously, the one on the left, 15,200, is bigger than 4,000. So there's my symbol. And here's our last example. Again, needs to go in your notebook. The speed of light is 3 times 10 to the 8th meters per second. If Mars is 2.25 times 10 to the 11th meters from the Sun, how many seconds does it take the light to reach Mars from the Sun? And we want the answer in scientific notation. Now, remember we have the distance formula, which is distance equals rate times time. Now, in this case, we're looking for time, so we need to solve this equation for t by dividing both sides by r. Now that tells us that time is equal to distance divided by rate. So that's how we're going to solve this. We know the distance from Mars to the Sun is 2.25 times 10 to the 11th meters. And we want to divide that by the rate at which light travels, which is 3 times 10 to the 8th meters per second. Alright, so we need to find out 2.25 divided by 3. That comes out to 0.75. Now we have 10 to the 11th divided by 10 to the 8th, so we subtract their exponents. 11 minus 8 is 3. So we have 0.75 times 10 to the 3rd. Now, remember again, it's not in scientific notation because this first number is not between 1 and 10. In order to make it between 1 and 10, I need to put my decimal point right here between 7 and 5, because 7.5 is between 1 and 10. Now, in order to get my decimal point back to the place where it was originally, I need to move it 1 place to the left. So I'm going to have to subtract 1 from the original exponent. So I have 7.5 times 10 to the 3 minus 1, which is 2. And that's the answer is in time in seconds. So it takes 7.5 times 10 to the 2nd seconds to reach Mars from the Sun.